Hello, my name is Anant Rajesh, and today I'll present StoryNet, our solution to SummerVal 2026 Task 4, Narrative Story Similarity and Narrative Representation Learning. To begin, the goal of this task is to determine how close a candidate story is to a given anchor narrative, not based on wording or surface features, but on deeper narrative structure. Three core components are used to define narrative similarity: abstract theme, course of action, and outcome. Obviously, these components don't always align. Practically identical events in stories with comparable abstract themes can result in polar opposite outcomes. The task explicitly ignores elements that make stories look similar but have no effect on narrative structure, like style of writing, names, locations, and length or detail of the text. For data, we use the official SummerVal 2026 narrative similarity dataset. The dataset consists of narrative text paired with human annotations covering both relative similarity judgments and single story embeddings. We wanted to see how current LLMs perform on this task. We provided the model with the anchor narrative and two candidate stories, A and B, and we asked it to decide which candidate is narratively more similar to the anchor. It is explicitly instructed to focus on themes, actions, and outcomes. When tested across the dataset, the LLM achieves an accuracy of 92.32%, but being a black box like system, is unable to provide any confidence metric. This provides us a reference point against which we compare our approaches. Before getting into our methodology, let's first examine some stories. We see that each story has its own events and their corresponding emotions. These are not independent but rather interact causally. As narrative similarity depends on these closely knit elements, we require a representation that preserves structured relationships. Thus, we adopt a graph-based symbolic representation. We decompose each story using an LLM through a structured three-stage prompting process that extracts progressively higher level of narrative abstraction. Stage 1 isolates the story's cast, assigning unique identifiers and annotating agency, attributes, and relationships. This establishes the narrative graph's foundational entities. Stage 2 extracts the story's event structure, labeling events with participants, emotional tone, and narrative purpose, and linking them through inferred causal relations. It also identifies parallel threads and thread intersections. Stage 3 traces emotional trajectories, identifies thematic elements, and maps the tension resolution arc, including escalation, crisis, and resolution. The output is a textually dense graph representation of the story. Using these three graphs, we explore three complementary approaches: a structural baseline, a semantic approach, and a Siamese GXN approach. Let's take these two stories as an example to illustrate how structural similarity works. Structural similarity compares the surface level topology of the constructed narrative graph by comparing the following properties. We begin with node overlap, which measures how many narrative units, characters, events, and thematic nodes are shared between the two graphs. This is computed using Jacquard-style ratio of shared to total nodes. Next, edge overlap compares the relational structure, how many causal, emotional, thematic, and participatory edges are shared. Together, these two metrics account for surface level alignment in narrative components and connections. Beyond simple overlap, we also examine how similar graphs distribute connections. In-degree similarity compares how similar nodes receive relationships, and out-degree similarity compares how similar nodes send relationships, capturing whether events and characters play structurally similar roles across stories. Finally, centrality similarity measures whether the most important or influential nodes occupy comparable positions in each narrative. This is computed using between the centrality values and a normalized difference formula. All components are combined using a weighted score. This is how the scores look when computed for the graphs. When tested across the dataset, structural baseline achieves an accuracy of 82.16%, lower than the one-shot LM baseline, but providing a clear interpretable measure of how the underlying narrative structures align. Unlike the LM baseline, this provides us with a confidence reference of 0.0953, which allows us to understand how subsequent methods perform, not only in terms of accuracy, but also in the stability and reliability of the decisions. Moving on to semantic similarity. Semantic similarity evaluates how closely two stories match in meaning rather than structure. After each story is decomposed by the three-stage LM pipeline, we obtain a story block containing characters, themes, emotions, causal chains, narrative functions, relationships, and event attributes. Semantic similarity then compares these facet by facet, capturing deeper narrative equivalence that graph structure alone cannot represent. We compute similarity across 7 semantic facets. Now, first being character similarity, compares how stories portray their characters, which includes role similarity, attribute similarity, and agency similarity. Second is theme similarity, which compares conceptual content, which includes semantic theme similarity and abstraction similarity. Third, emotion similarity, which compares emotional trajectories, which includes arc progression, distribution similarity, and change pattern similarity. Fourth is causal similarity, which compares cause effect logic, which includes relation similarity, strength similarity, and temporal gap similarity. Fifth is functional similarity, which compares the narrative purpose of events, which includes structural similarity and beat overlap. Sixth is relationship similarity, which compares how characters interact, which includes type similarity, evolution similarity, and power dynamic similarity. And finally, we have event level similarity, which compares what happens in events, which includes type similarity and tone similarity. Event textual descriptions are intentionally excluded to avoid surface level bias. The final score is obtained through a weighted aggregation, where the weights are learned via logistic regression using a difference vector of the similarity scores and perturbed to improve confidence scores. When tested across the dataset, semantic similarity achieves an accuracy of 92.83%, outperforming the one-shot LLM baseline, while also improving on the confidence by 0.03 as compared to the structural baseline. This shows that integrating facet-wise semantic information enables the model to capture deeper narrative correspondence. Now that we already have graphs, why not use networks built for them? Our previous methods use either structure or meaning while completely ignoring the other side. To overcome this, we encode the entire story graph into a vector space via Siamese GXNs. Let's now understand the pipeline used. Each story is converted into its corresponding graph and then undergoes the pre-processing step. Each node/edge has rich textual attributes. We embed these into 768 length vectors using sentence transformer. This gives us the final length vector of the size num features, 768, where num features is dependent on the story. We use triplet loss to build a shared GNN encoder for all three, anchor, positive, and negative. Now let's see how we convert the node-wise 768 dimension vector into a 128 graph dimension vector for each story. We explore two methods: graph convolutional networks and graph attention networks. So graph convolution networks, each GCN layer performs message passing, aggregating information from neighboring nodes. We use two spectral convolution layers followed by global mean pooling to obtain a fixed size 128 dimension graph embedding. This uses triplet margin loss, which enforces embeddings of similar graphs, anchor positive pairs, to be closer to the embeddings of dissimilar ones. Next is graph attention networks. The graph attention network introduces attention-based message passing, enabling the model to learn which neighboring nodes matter most when aggregating information. Each node computes attention scores over its neighbors using multi-head self-attention, allowing it to dynamically emphasize narratively important edges such as key emotional transitions, causal links, or central thematic roles. Let's analyze the embedding space of the GAT. We can clearly see that stories look randomly sprinkled over. This is because the GAT is trained using triplet loss, which optimizes relative distances within each triplet rather than enforcing global clustering across the dataset. As a result, we observe numerous small triplet clusters rather than a coherent large-scale groupings. This behavior is expected and desirable, as the model focuses on preserving local narrative similarity relationships rather than aligning all stories into a shared embedding manifold. The results show progression from structural comparison to semantic and graph-informed methods. The structural baseline is accurate but lacks confidence due to its inability to account for semantic nuances. The LLM baseline performs well with language model embeddings but lacks interpretability. Our semantic similarity model slightly outperforms the LLM baseline, demonstrating the value of weighted multifaceted narrative reasoning. The GCN model has higher confidence, indicating stronger internal consistency. And finally, the GAT model with the highest accuracy and highest confidence confirms that attention-based message passing effectively captures cross-facet dependencies and narrative coherence. Clearly, our best semantic and GAT model outperform the LLM baseline. But let's take a more in-depth look into where this is happening. The LLM's baseline misjudged text B as close to the anchor due to the high lexical and surface level overlap. Text A, however, aligns more closely with the anchor in its causal progression and narrative resolution pattern, where conflicts escalate and resolve around a central tension node. The semantic model correctly identifies this correspondence, assigning higher similarity across causal, narrative function, and emotional arc dimensions. These subscores highlight that both stories share parallel emotional trajectories and functional beats leading to resolution. The GAT encoder reinforces this alignment as seen in the embedding space, where the anchor positive pairs clusters tightly while the negative remains farther. Attention mechanism allows the model to focus on salient nodes, particularly those linking central tension and key events, capturing narrative importance rather than superficial lexical overlap. Now let's examine where our semantic similarity is lacking compared to our GAT pipeline. The semantic model misjudges text B as close to the anchor due to its dimension-wise aggregation, which overweights local overlaps and fails to penalize deeper inconsistencies. The GAT encoder correctly selects text A with a confidence of 0.178. The anchor positive distance is smaller than the anchor negative distance, indicating that the GAT captures global narrative coherence rather than isolated matches. Its attention mechanism focuses on structurally crucial nodes, downweighting diffuse elements, resulting in a more reliable comparison. There are also points where semantic similarity seems to beat the GAT. Let's examine. The semantic model correctly identifies text A as more similar to the anchor, while the GAT model predicts text B with high confidence. The semantic model succeeds because its fine-grained aggregation captures strong correspondence across theme and emotion. Both narratives share core themes and follow compatible emotional and causal trajectories. In contrast, the GAT encoder misclassified the pairs with a substantially larger anchor positive distance than anchor negative distance. This indicates that the GAT overweights structural density and node connectivity when forming graph linear bindings. For the conclusion, our study shows that narrative similarity requires combining structural alignment with deeper semantic reasoning, and that purely text-based LLM judgment miss important causal and functional signals. By decomposing the stories into symbolic graphs and learning representation over both graph topology and facet level meaning, we obtain models that are not only accurate but provide more higher confidence and interpretability.